So we said that any contact force that pushes down into the surface, the normal force pushes back in which direction? Perpendicular. I know we did this. That's why we're doing it again. No, because it's conceptually like if you don't get this key points, it makes everything else harder, and so it's very important that we get this. So we're gonna review for like 10 seconds because we didn't spend that long on it, right? So it's gonna be really fast. We have then gravity. Gravity goes down, but towards the what of the Earth? The center of the Earth, and so it goes straight down for all our drawings, straight down as we can go. I don't know how else to describe it. Um, Now, if I were to add them, how would I add them? Tip to tail? Okay, so when I add them tip to tail, I'm just going to slide it over. I'm going to take this and translate it. Okay? I'm just going to slide it. And so it goes down here, and then we add that up here. And then we find out, hey, look, that makes sense because the box started here, but really its motion goes which way? That way. That way down the face of the ramp, okay? And that makes sense, right? Objects, and we knew that before because you could have probably filled this out. In the absence of friction, describe what will happen to the block. We said that it would go down the face of the ramp. Perpendicular to the surface. I'm not going to write that. Perpendicular to the surface, right? I could write that there too. And so we know that this is the force due to gravity. And how far did we get in this class? Did we say that this is a right angle?
Yeah.
Did we say that this is a right angle?
Yeah.
Did we start rotating our paper?
Yeah.
Okay, so what if we start rotating our paper, what ends up happening is that this 30 degrees right here, this was flat. This right here is flat. The bottom of the ramp is flat. This is straight down gravity. So these are what to each other? Right? It would make a little cross right here. Okay? Not just that, but this is perpendicular to the surface by definition right here, right? There's a little cross right here. So if I take this paper and I say, let's rotate it, and let's make this ramp flat. So the ramp that was at 30 degrees, I make it flat. Well, now this one is straight up and down, and this one is straight side to side, and this is now at 30 degrees from where I'm at. So this is our 30 degrees here. This is our similar triangle. Be very careful. A lot of people think that because I give you a 30 degrees here from the horizontal, that you're going to have 30 degrees from the horizontal over here, but that's not the similar triangle. It's this one. That's the 30 degrees. Okay? And the other one over here is complementary to it. So this is our theta, and this is the similar theta to it, or the same theta, I guess, at this point, the same angle. Okay. So what is the net force parallel to the incline? What do we call the net force? So the net force parallel to the incline is with the face of the ramp, right? So I'm going to call that x. What does that equal? What is the force? What is the sum of all the forces? Which one is it? Red, green, or blue?
Red.
It's the red one, right? It's with the face, right? So we could call that the force of gravity. Sine theta. If we in geometry learned that sine was opposite over hypotenuse, the hypotenuse sine theta would give us this opposite. Okay? According to Newton's laws, what does this net force equal? So the same net force equals ma, right? That's how it moves down the face of the ramp. Literally, it's the mass that accelerates. And if we use Newton's second law that you learned in middle school, F equals ma, we can say, now we know how it's going to slide down the ramp, how it's going to accelerate. So we literally can take that force and say, how is it going to move? And so if we set these two problems equal to each other, if this net force that it slides down the face of the ramp based on gravity, and this net force, that's how we can actually measure its acceleration, we could say that mg, which is fg, sine theta, equals ma. This mass is the mass of the box. What's this mass then? Still the object, right? Still the box. So if we have mg sine theta equals ma, to find the acceleration, what would cancel out? Mass. Let me just switch colors so we know. A equals g sine theta. So what doesn't change? Let me rephrase this question. If I change the mass and I have two items just sliding down ramps, they should accelerate the same. Okay. Now, that's not true with all objects. Some objects are round, but I said sliding. Okay. We're on a frictionless surface right now. If I have a perfectly smooth surface, the only thing that affects how and the speed that we go, or the change in speed that we go, is gravity and the angle that you're at. Okay? The heavier thing doesn't move any faster or slower because we've got more gravity force to push more mass. Okay? It's just the relative acceleration is still the same. Kind of like when we drop something, everything falls and picks up speed at the acceleration due to gravity, right? So it's 9.8. What happens to the value of the acceleration as the angle increases? Gravity should. The acceleration due to gravity increases based on that angle. So the acceleration in general increases as well. I'm going to write more information there. That's why they give us an extra line. But we're going to solve for the acceleration at different angles. So if we have A equals g sine theta, that's what we said above, I can just plug in 9.8 sine 30, 9.8 sine 45, 9.8 sine 60, 9.8 sine 90. How about I do the first and last one and you can do the middle too? So what'd you get for 9.8 sine 45? 6.93. And then what did you get? 9.8 sine 60? 8.49. All right. And so the other numbers I'll report back 4.9 and 9.8. All right. Is there a net force perpendicular to the incline? So I'm talking about, is this box going to fly off to the sky? Is this box going to sink into the ground? So there's no acceleration. So is there a net force perpendicular to the incline? No. So solve for the normal force using the variables. The normal force, well, if there's net force in the y direction flying off the ramp is equal to 0. And then we look at all of our arrows. We've got an up arrow and a proverbial down arrow kind of sort of right there to balance it out. We are talking about the force normal minus mg cosine theta. What I'm saying right here is that the normal force is opposed by the gravity proportion that goes straight into the ground. The amount of gravity that goes into the ground is opposed by the normal. And that's really, the normal is designed to eliminate the gravity that's pushing straight into the ramp. I'll say that one more time because it's kind of confusing. The normal pushes back however much it needs to, and so the gravity that pushes into the ramp is opposed to by the normal. Well, that's what I have here. Normal versus the gravity amount that pushes into the ramp. And this is also equal to the net force in the y direction. Yes?
Why do you use mg there but then fg in other place?
Fg equals mg. Just as a general rule, the force due to gravity equals mg. They're practically interchangeable. What I have noticed on the AP test is a lot of AP tests, that keys that I've seen will label Fg and then they'll start using mg in their work. And so as long as you, I would appropriately label all my forces as force due to gravity, so Fg. But automatically, you know that it's a field force, so nothing gets in its way, nothing will change it unless we start manipulating the gravitational field. And I don't think that happens at this level of physics. I can't imagine us like having anti-gravity fields and bubbles and stuff like that. That'd be weird. That's like science fiction for us. Okay. And I think that's kind of cool that we can investigate science fiction, but I've got to teach you the basics first. So what happens to the value of the normal force as angle increases? Wait. We didn't solve for this one. Solve for the normal force. If f of y we said was 0, right? I can just move half of this to the other side, right? I'm just going to say force normal. I'll just put it on the next line. Force normal equals mg cosine theta. Okay. I could move over the mg cosine theta because I'm just going to add it to both sides. So that's where it is. Force normal equals that. So what happens to the force normal? If this is true, what happens as I increase the angle? What happens to the pushback force as it gets steeper and steeper and steeper? Does my slope push back as much? Does my contact force push back as much if it gets steeper and steeper and steeper?
Yes.
The normal force decreases. And n will approach 0. And the easiest way to demonstrate this is I've got my object here and it slides down the ramp. Okay, so here's my ramp and there it goes, it slides across, slides down. What happens if I get steeper? Does the ramp face push back as much? Let me put it this way. Does the ramp face push back at all here? Right? It just falls. So the ramp face only pushes back when gravity helps it push into the face of the ramp. Okay? Does that kind of make sense? Gravity has to push down. The ramp face pushes back only as much as it needs to.
So Mr. K, does it cap out at like 45 degrees? Where's the maximum amount?
Let's actually solve for it then. We said that force normal equals mg cosine theta. And so really cosine maxes out when cosine is 0. The mass of the block in the picture above is 10. So I could say 10 times 9.8 times cosine 30. 98 cosine 45. Cosine 60. And cosine 90. I already multiplied those out for you. And I can do the last two for you. if you've already started. Mr. Kwan, you're picking the easy ones. Yeah, duh. Use a calculator. Um, 30 is opposite of 60, so this is 85. And then this one is 69. I'm just using the chart down here. And then I'm using the opposite angle, or the opposite function with the opposite angle. So sine 60 is equal to cosine 30. But it's 10 times bigger. So when does it max out? It maxes out at 0 degrees. It would be 98 newtons, right? And it drops to 0 as we get steeper and steeper and steeper. The ramp doesn't push back as much. Yeah. Its forward speed wouldn't be as... Oh, I don't know. I don't know how to describe it. All right.